Good morning, everyone. Today, in this class, we are going to look at the one specific wave, which is sound waves. And I know this is going to be note day 5, not day 4. Day 4 note on interference, we will cover it when I come back next week. Okay? So, now let's start with sound. To refresh your memory, we have to remember that sound is not a transverse wave. So the particle in a sound wave does not move the same way as a particle on a rope. Sound is a longitudinal wave. Okay, so longitudinal wave produced by vibrating objects. Imagine a flat surface moving back and forth inside a speaker. The vibration of the speaker surface results in a compression and rarefaction in the air. So for example, when I speak, my throat vibrates and it compresses the air, and eventually that compression and expansion of the air molecule travel to your ear. Inside your ear, there's a eardrum. And your eardrum will pick up that vibration, and your brain collects your eardrum and they turn its vibration into a signal which you perceive as sound. Now, eardrum, unfortunately, is not a piece of muscle that you can, take advantage of. If you listen to really, really loud music, or if you happens to be very near an explosion, sometimes the air compresses and expands so much, and the vibration is so big that your eardrum can actually burst. Now, luckily, your eardrum is self-repairable in most circumstances. That means if you give it some rest, even if your eardrum bursts, you give it some rest, a few months later, it should repair itself in most circumstances. But if the damage is too great, it could be irreversible. That's why I would strongly suggest when you listen to music, turn the volume to an appropriate level. Some people in class, when they are working on their own work, they listen to music through their headphone. Well, obviously, if I can hear your music all the way from where I'm standing right now, that's way too loud for you because you actually have the earphone in your ear, and I can hear it from like 10 feet away. Okay, so make sure you don't listen to music with like uncontrollably loud noise. Okay, now another thing is if you need a visual representation of what the wave actually look like, you can actually go and visit our class webpage. Our course webpage has been recently updated, and it will actually now show you a lot of information on these waves, a lot of animations on these waves. So for example, if you go to our course webpage, which we are going to right now, and you look at, let's see, okay, so let's say you go to Physics 11 and you select wave and sound, and scroll to the bottom, you'll now actually see quite a lot of animated GIF. Okay, a lot of these GIF animation. For example, we're talking about sound wave, so well, there we go. Sound wave on the left panel. Oh, it's really hard to stop exactly there. I overshoot it multiple times. There we go. So ignoring the wave on the right, so those waves on the left are how sound wave propagate. Okay, so on the left hand side, so you look at like these wave in here, so these are sound wave, right? So your eardrum will be on the right, and someone vibrating a surface will be on the left, and the air compresses and expands and it travels to your ear. Okay, so just a reminder. Now let's go back to the note. Now it turns out, so in sound, we have to put different kind of classification compared to other type of wave. So in a sound wave, let me get access to this. In a sound wave, high frequency means high pitch. Low frequency, and get access to a no pitch sound. Okay, so the frequency of sound. Okay, okay, so the pitch of sound is determined by its frequency. High frequency means high pitch, which in a music term is called tremble. And low frequency sound is when you have no pitch. And in a frequency term, that's your bass. So tremble, so high frequency sound will sound like this, ah, and low frequency sound will be like ooh, like that. So high pitch and no pitch. Now human ears, on the other hand, cannot actually hear all the frequency. We have limitation on what we can hear. So let's take a minute and watch a YouTube video, which should be on the course webpage on under the Ph11 and waves, and let's study what is the maximum and minimum audible frequency for human ears. Now, different animal might have a different value, but then, for human, we have a maximum and minimum audible frequency. Okay, so you should pause this video right now and go to the website and listen to the human audible frequency range YouTube clip. Okay, so pause the video right now. Okay, welcome back. So I assume that you already watched the video, which has the audible human frequency. And what we have discovered is that human, generally speaking, can hear somewhere between 20 hertz to 20 kilohertz. Now 20 kilohertz means 20,000 hertz. Okay, and even anything that has higher frequency than 20,000 hertz, we have trouble hearing. And anything lower than 20 hertz and a sound that's really low pitch, we have trouble hearing also. Okay, now, for example, well, in a side note, dogs can hear both lower and higher pitch sound than human. That's why we have dog whistles. So dog whistles produce a sound that is in the 30,000 or the 40,000 kilohertz, so only dogs can actually hear the whistle blowing, human cannot. Now, and also sometimes, right, if you have dogs, you probably know what I mean. Sometimes your dog will bark at some random locations, and there's like nothing over there. Sometimes you see a dog barking at like the corner of the wall, and there's like nothing at that corner. You're wondering, okay, so what's the dog barking at? Well, it turns out that sometimes in your house, due to various, electrical or mechanical properties, sometimes your house actually produce sound that are in a wavelength or in a frequency that's higher than what human can detect. So you don't hear it. Maybe it's the water going through a pipe, and maybe some electrical current going through a wire, but you cannot hear it because the frequency of that is too high. But the dogs will pick it up. So the dog actually picks up some sound that humans have trouble hearing. So sometimes you think the dog is barking at like, ghosts, but it's actually barking at some mysterious sound that has higher frequency than what we can hear, and then there's reason for it. Or maybe the dog is actually barking at a ghost, okay? So pick your explanation. On the other hand, talk about cats, right? So cats, on the other hand, cannot hear low frequency sound. Okay? So what does that mean is, now you look at the cat, so the cats can only hear between 60 to 65 kilohertz. That means high frequency sound the cats are really sensitive to. I guess that's why when we talk to cat, we go like, oh, kitty, 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 like that, right? So high frequency sound the cats are really sensitive to, better than human. But if you look at the low frequency range and compare that to the human's frequency, human can hear as low as 20 hertz. Cats start at 60 hertz. That means if the sound has too low of a frequency, the cats will actually unable to hear it. So that means if you talk to your cat, for example, like, I guess I cannot actually produce a sound that is as low as that frequency, but I can try. If you talk to your cat like this, which has a very low frequency, your cat will completely ignore you. Not because your cat does not love you, because your cat cannot hear you. Okay? Now, I know the sound I just make is probably a lot as low as it should be, but you can use the program again, right? So the video that you just watched, you can go back and listen to what like 40 hertz sound like. Your cat cannot hear that one. Okay? So sometime when you talk to your cat, people usually use higher pitch noise, higher pitch voice to do that. There's a reason, because your cat responds really well to high pitch noise, just not too well to no pitch one. Okay, so fun facts, right? Now moving forward, okay, so that part is good. So we are going to look at speed of sound. Now, last time we looked at speed of other kind of waves, and we determined that, okay, so the higher the density usually means that the wave moves slower. But sound is not a transverse wave though, right? Sound is a longitudinal wave, which works exactly the opposite way. So for a longitudinal wave, like sound wave, for example, the speed of the sound wave is actually dependent on the medium. Now usually, the more dense, the faster the sound wave will travel. So the speed of sound wave in solid beats the speed of sound wave in liquid, which could be water, which beats the speed of sound wave in gas, which is air. So the speed in, for example, steel is faster than the speed in water, which is faster than the speed of sound in the air. Well, then how fast does sound travel in the air? Well, depending on temperature. Because temperature changes the density of air too, right? So sound travels faster when the temperature is higher. So it turns out that at room temperature, sound travels at 344 meters per second at room temperature at sea level. What is room temperature? 20 degrees Celsius. But if the air is really cold that day, like 0 degrees Celsius, then sound only travels at 331 meters per second. Okay? So there's a small difference between that. Now, so once we know that, we can actually get the equation. So people have been measuring how fast sound travel at different type of temperature, and they come up with a trend. The trend is the sound travel faster in warm air compared to cool air. The speed increases by about 0.6 meter per second for every 1 degree Celsius of temperature increasement. Okay, so every time the temperature goes up by 0.6 meter per second, the speed of sound, the temperature goes up by 1 degree Celsius, the speed of sound goes up by 0.6 meter per second. So then we can get the equation. So the speed of sound is 331 meter per second, which is like a base value, plus 0.6 times the temperature of that day. So this T right here is not the period, it's the temperature. Okay? And it's temperature measured in degrees Celsius. Please don't use Fahrenheit. Okay? And now this equation should be on your formula sheet. But I guess if you want to be safe, since we do have a unit, we do have a symbol called period, which also use T in this unit. Make sure there's a different, you know the difference between this T and the other T. The other T is period, which is measured in second. That's how long the time it takes for the wave to travel one cycle. Whereas this is T as in temperature T, and it is measured in degrees Celsius. Okay, so we're going to go through a few examples. Now, I know that on to the right there's a box for the Mach number, which we're going to ignore for now. We're going to go through a few examples, and then we're going to come back to that box, okay? So, example, what is the speed of sound in the air at 5 degrees Celsius? Well, that's easy. Directly application of the equation. So 331 is the base value, 0.6 for every degree Celsius, and now we have 5 degrees Celsius. So that 5 times 0.6 is 3, so we add 3 to it, 334 meter per second. Okay, so that's an easy one. Now, to the next one. Okay, so a bass guitar produces a 70 Hz sound wave at a room temperature. Okay, wait, at room temperature means at like 20 degrees Celsius. Determine the length of this sound wave. So in order to do this, we actually have to use two equations. So first, we have to find out how fast is the sound wave in this room. which is 331 plus 0.6 times the temperature. Now the temperature is 20 degrees Celsius, so we can put it in here and get the speed of the sound at room temperature. Or most people actually memorize the speed of sound at room temperature, which was the first value we wrote down, 343 meters per second. It was in the last paragraph that we worked on. So if you memorize it, it's okay. You don't have to work it out. Otherwise, work it out this way. Okay. You say, okay, so now I have the speed of the sound wave. What do I do to get the length of the wave? Well, you do remember that for any wave, we learned last class, any wave speed can be calculated by lambda f, the wavelength times the frequency. So the speed of sound is a wave. I mean, sound wave is a wave, right? So therefore, we can say, well, the sound wave is 334 meters per second in terms of speed, and it's equal to lambda multiplied by the frequency, which is 70 hertz. So if you take those two and divide them, you get 4.9 meters as the wavelength. Okay, so in this example, we had to use two different equations. We had to use a speed of sound wave, and then we had to use the wave equation, which was from last day. So now is a very good time to consolidate all these speed equations because there are now two, but if you remember on day one, we actually had another speed of wave equation. Now let's write them all down. So first, we have distance over time as the first speed equation, and that was learned in kinematics. Now this one, distance that you travel over time, is for everything. Okay, then last two classes, we pick up this equation, which is called the wave equation. This equation has wavelength and frequency. This equation only works for speed of a wave. Today, we pick up another one, which is the speed of sound wave. Now this one works for sound only, in the air only, so 0.6 multiplied by the temperature. So this one is for sound wave only. So if you have a wave traveling on a rope, then you can use the first and the second equation, but you're not allowed to use this third one. So this one is for sound wave only. Okay, so this one is only for sound wave. Now, so that means if you're working on sound wave, there is actually a possibility that you have to use more than one of these equations, because sound wave, of course, satisfies the last equation for sound wave only, the second equation for any wave, and the first equation for anything. But if you have a wave traveling on a rope, a wave traveling on a slinky, a wave traveling, in space, like speed of light, then the only equation you can use is the middle one, because the middle one works for any wave, whereas the speed of sound equation only works for sound. I mean, hence the word speed of sound, right? Okay, so I want to go through another example before we go back. So let's go to the next page to look at another example first. Okay, so this question is asking for two things. A 250 Hz sound wave is 1.42 meters long. Determine the speed of the sound in the air and also what is the air temperature of that day. Okay, first, 250 Hz is a frequency, 1.42 meter is a wavelength. With frequency and wavelength, we can use the second equation that we wrote down earlier. So this goes with any wave, which is lambda f. So the speed of a wave is lambda f. So we put 1.42 meters and 250 hertz to get, well, the speed of the sound is 355 meters per second in your calculator. Now, so that's part one. That's also one of the questions. So now we have to answer part B, which is what is the temperature of that day? Well, okay, so if it involves temperature, then I guess I lead the other equation that has temperature on it, right? So speed of sound wave is equal to a base value 331 plus 0.6 times the temperature. So we're looking for the temperature, but we got a wave speed from another method. So we will substitute wave speed in here, which is 355 equals to 331 plus 0.6 T. Solving for T, the temperature of that day. Be careful though, when you solve for this T, make sure the 331 is the first step to go. And then, of course, subtract 331 by 355 divided by 0.6, and you get the temperature of that day to be 40 degrees Celsius. Pretty hot day. 40 degrees Celsius. All right. Now, moving back to the Mach number from the previous page. So the Mach number is a ratio that people make up to compare the speed of another object to the speed of sound. So when people say, hey, this airplane can actually fly at Mach 2, that means it can do double the speed of sound. Or you can say, oh, this bullet is going at Mach 7.5. That means it's traveling 7.5 times the speed of sound. So Mach number, which is, you can use it as an equation like this, is v, the speed of the object that you want to compare to the sound, divided by the speed of sound in, I guess, room temperature, right? Because we couldn't possibly know what temperature of the day is. We'll just use room temperature of speed of sound, which is 343 meters per second. So just compare that, divide it, and then that is your Mach number. So for example, we'll do this one example, which is really quick. If you have a cruise missile that can go at Mach 0.8, how fast is the missile going? Well, that means it's going at 80% of the speed of sound, right? So the Mach number is equal to the speed of the object divided by the speed of sound of that in room temperature, which is 343. So if we know the Mach number is 0.8 and we know the speed of sound on that day is 343, then figuring out the speed of the missile should be very easy, of 0.8 times 343, which will be about 274 meter per second. Okay. Now, but of course, you have to be careful though, because, for example, if an object goes faster than the speed of sound, something weird can happen. It's called sonic boom. So if you go faster, if you go above Mach 1, then you actually create something called sonic boom, which we will look at again in a couple of days. Okay, so then let's talk about just some general information about sound volume. So the volume of sound, which is its intensity, is based on the amplitude of the sound wave. Okay, so the higher the sound wave is doing this, like the higher the amplitude, the louder the sound is. Okay, so the higher so in here, higher amplitude wave means more energy. More energy means louder volume. Okay, so higher amplitude sound wave means it has more energy, which means it is louder. Okay, so we use a scale called the decibel scale, and the unit is decibel, dB, to measure the intensity of sound. It's actually just a very fancy way to relate the decibel to the power delivered to your ears by the sound wave. So technically, decibel is an obscure version of power. You can think of it like that, but it's not exactly the same. So one way to think about this is, what is absolute quiet? Like no sound at all. It's very difficult to achieve that in our environment because there's always going to be some kind of background noise. Even if you're in a room with like no one talking, you can still hear
the emptiness. You can hear this like very faint but persisting sound in the environment, because even though you're in a room with no one talking, the environment that you're in makes sound, the ground makes sound, the wall vibrates when the wind hits it, it makes sound that way too. So we don't really, I mean, technically speaking, if you go to space, you can have like an absolute no sound environment. But on Earth, that's really hard to achieve, right? And plus, our ears are not that sensitive, so it's not practical for us to talk about like an absolutely no air movement. I mean, air movement is sound. So in order to have no sound, you have to have no air movement, or better, no air. And that's very difficult. So we set up our sound system on Earth using not like a no air movement as the base, but we use the smallest sound that human ears can pick up as the base level. And that is a level 0. Okay, so a level 0 sound is the smallest, faintest sound that human ears can actually pick up. It's an arbitrary thing, okay, and it's called 0 decibel. And then for every increase of 10 decibel, the sound is actually 10 times more intense. That means 10 times more energy. Not one, not. So for example, from 0 decibel to 10 decibel. Now, so what does 10 decibel sound like? Breathing. Just you regularly breathing. Okay, that's 10 decibel. And what about 20 decibel? Now, if you look at 20 decibel, a sound that has a intensity of 20 decibel, you think it's 20 times louder than the bass, right? No, it's actually 100 times louder than the bass, because this is not a linear scale. Decibel is actually on something called a log scale, which means every increase of 10 is actually 10 times, not 10. Okay, so from 0 to 10 is 10 times more energetic, and from 10 to 20 is again 10 times more energetic. That means from 0 to 20 is actually 100 times more energy. So now I don't have a reference for 20 decibel, but I do have a reference for 30 decibel. 30 decibel is when you whisper to someone. Okay, when you whisper to someone, when you're actually saying something, but you're saying it in such a way going like, hey, how are you? Like whispering. Whispering, not even talking regularly. Whispering is 30 decibel, and it's 1,000 times more intense compared to the base level. Now, I do have some extra one for your reference. So regularly talking, right? So regular talking to people is about 60 decibel. Okay? Traffic, if you sit next to like a street and you hear the traffic outside, it's about 80 decibel. A train passing by you is 100 decibel approximately. Shouting really loud could be 110 decibel. Now, the thing is, after at around 100 decibel, your hearing will actually suffer damage. Okay, so talking to people for a long time even doesn't damage your hearing, but anything that's above, approximately 100 decibel or louder is going to give you hearing loss, like, a permanent, sometimes hearing damage, sometimes it's like a temporary one. So for example, a train, like a very, very loud train passing by you, after 15 minutes of continuously standing next to that, it's going to cause permanent hearing loss. Now, that's why, conductors who are, controlling the trains and who works on the train station, they have to wear proper ear protection sometimes. Shouting to people, like shouting to each other, 110 decibel approximately, permanent hearing loss. Some percentage of it, of course, right? You're not going to lose all your hearing at once, but you will suffer some levels of hearing loss after 2 minutes. And 140 decibel is when someone, for example, have firecrackers or explosion next to you, and that will actually cause immediate hearing loss with pain. A lot of pain. Now, of course, again, you do not have to know exactly the level. I mean, you can always refer back to this chart. You do need to know that every increasement of 10 decibel is actually 10 times more intense, not just 10. So 100 to 30, for example, 0 decibel to 30 decibel, a sound that's 30 decibel is not 100 times more intense. It's not 30 times more intense. It's 1,000 times more intense. Okay, and you do need to know that, approximately after like 89, like after 100 decibel, you'll suffer hearing loss as a certain scale. Now, the last, okay, so unfortunately, right, it's actually very unfortunate that the last bit in here called bit, no pun intended, is usually demonstrated. If you are in class, then I have two speaker and I play the two speaker at different frequency, and then you can hear the sound combining into one. But it's very difficult to do it in here. I'll try to set it up, but basically what this is doing is that when you have two sound, that are playing with slightly different frequency in two different speakers, okay, then the two sound will actually interfere with each other, and what you will hear is the combinations of the two sound. So waves can actually reinforce each other if they have the crest and the crest lining up. For example, in this case, then it will reinforce each other because you have the crest of one wave meeting the crest of another wave, and then you create a super maximum mixture. So this first wave 1 plus the wave 2. So wave 1, for example, could be the sound wave coming out from one speaker, and wave 2 are the sound wave coming out from another speaker. So when they line up perfectly, okay, then they create a reinforcement sound that is even louder than each of them individually. But if the two wave does not have exactly the same wavelength, then somewhere down the line, you're going to get something like this. Look at this point. At this moment, wave 1 is at a minimum, but wave 2 is at a maximum. So this is like what happened when you have like a negative number adding to a positive number, and what you get at the end is a result of almost zero, very low amplitude. Now remember, for sound wave, high amplitude means loud and low amplitude means soft, right? And low volume of sound. So if you are hearing only wave 1, you will hear a continuous tone of wee. And if you only hear wave 2, you will also hear a continuous tone of wee, but at higher frequency, because for example, in this case, wave 1 is at 40 Hz, wave 2 is at 50 Hz. So if you only hear one speaker, one sound at a time, you'll hear a continuous tone of that frequency. But what happens if you place those two speakers very close to each other so that they have a chance to affect each other? Then the two waves will sometimes help each other out and sometimes destroy each other. And that will create a very funny looking sound profile, which sound like this. So what it will sound like is sometimes loud, sometimes very soft. When the two waves are adding up, lining up max to max, the wave sounds very loud. When the two waves when the two wave happens to be adding maximum to minimum, then the wave sounds really soft. So instead of hear the wee and the wee continuously, you will hear wee 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 wee, and that is called a beat. Okay, so I'll try to see if we can find something to replicate that. Now, hello. Now, I have two. You should see on the screen right now. I have set up two online sound generator. The one on the left is going to generate a 440 Hz sound, that means, which is a A4 on the musical note. I will let you hear just the 440 Hz right now. Hopefully you can hear that. So let me increase the volume so maybe it can be better right here. So let's hear the 440 hertz again. Now let's hear the 443 hertz. Now, as you can see, because the frequency are so equally matched, right? There isn't much difference between the two. Let's hear it again. 440. 443. Not much different, right? Okay, now let me turn both of them on at the same time because my computer has the two speakers right next to each other. So I will turn on the 440 first, and then I will turn on the 443. 440 is on. Now turning on 443. You hear that? Now shutting off 440. Shutting off 440. Turning it back on. You hear that beat? Now I can actually increase it. So you hear that beat? Okay, so we want two things to notice in here. Number one is that when the two source of sounds are played at slightly different frequency, then you will get a beat, right? You get a beat because one sound is interfering with the other sound, and sometimes they add up. At some point, they destroy each other. So you're receiving a sound wave that is sometime at a maximum, sometime at a very soft tone. Now, the frequency of your beat is actually dependent on the frequency difference between the two sources. Okay, so when the two sources, for example, in this case, right now, 440 and 445, so there's a difference of 5 hertz, right? So when you listen to the beats will have a frequency of exactly 5 hertz. Now, but what if the frequency of the two sounds is actually closer? So for example, what about 440 to 441? There's only a difference of 1 hertz, and the beat will now be a lot slower. This is a beat of 1 hertz, only 1 cycle per second. What if the frequency difference is a lot higher? What if one is 440 and the other one is 460? So now there's a frequency difference of 20 hertz. That means the beat should be at 20 cycle per second also. It's almost too difficult to pick up with the 20 hertz frequency difference. Now, I think this online tone generator should be on our course web page. So if you open, so you can actually go ahead and when you have time, if you want to do that, is open two tab, not two window of that same web page side by side, and just make it so that it only takes half the screen for each window. Don't do tab, because if you do tab, you have to go back and forth, right? Actually do two separate window of like Chrome, whatever browser that you're using, and make them half the size on your screen so that you can turn one on and turn the other on. You can replicate this effect with your own computer. Okay, it's very easy to do. Now let's go back to our notes and finish it off with the equation, just mentioning the equation. So the beat frequency equation is extremely easy to handle. The frequency of the beat sound that you will hear, that tone of woo 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 woo, is just the difference in frequency between the two waves. And we don't want to look at the negative number in here, so just please use the big one and minus the small one, and that's all you need to do. Okay, now so that's it for the sound wave section, and I will post everything on the course webpage as usual. Goodbye, everyone.